Okay, I tried to come up with some things that I'd really like to bring across to an audience like this about climate change, and it ends up being sort of a scattershot thing, and it's not all that long of a presentation. So I'm going to try to cover a few high points. So my outline shows that I'm going to start out with some overarching concepts and then go on to global influences of greenhouse gases. Talks some about really the main focus of my work, which is Great Lakes water levels, projections for long term, and touch a little bit on algal blooms and hypoxia and fish growth. This previous presentation really did a lot of the groundwork for that. So my perspective, I'm a science geek, and I'm hoping that most of this audience are scientists of some stripe and will kind of share in these attitudes. So this slide is something I really tend to present to more general public type of audiences, but I thought I'd share this with you and hope that you'll agree that Al Gore isn't putting me up to anything, and it's not about capitalism being evil. It's just we're going with what science tells us about climate change. Now, when you're talking about climate change, you really need to put theory and observations together. And one of the public presentations that I gave several months ago, I actually had the Western Bureau Chief of National Public Radio in the audience. And he said, "I hate that word theory when scientists use it." So instead of saying theory, sometimes I say doing the math. So we have math that backs all this up. And but on the other hand, we also have observations. So this first bullet point talks about one of the observational things. And we're now up to 30 full years in which every month has been warmer than the 20th century average for that month of the year. So that's, statistically, that's like flipping a coin and getting heads 360 times in a row. Very unlikely to happen by chance. But then going back to the theory, we have an understanding of how these gases work in the atmosphere and can do some of the math and figure out that is one of the real causes behind it. So putting those together really is a much stronger argument for this human cause than having either of those arguments on its own. On the observational side, though, when you narrow only to the Great Lakes region, there's a little more of a mixed signal in there. And that's really part of the nature of the beast. When you get down to more specific regions, the noise in the system has more influence, and there's not quite such a strong signal to noise ratio. So another thing I wanted to bring across is the long history behind this understanding of how greenhouse gases work. And don't worry too much about the equations on here. The real point behind the equations is that these have existed for long periods of time, in some cases greater than 2 centuries, and have stood up to scientific scrutiny for that length of time. And also, these equations can fit in a fairly small amount of screen space. So they're well understood by a lot of scientists, and so just pieces of this puzzle of our understanding of climate change have been accumulating for a long time and have stood the test. Now, when we get down to this bottom line here, which I call putting it together, that's really the concepts behind, in the case of Tyndall, 1859, he was the person who really came up with the understanding of the greenhouse effect. He was thinking of it more in terms of the natural part of the greenhouse effect, but his understanding was that water vapor is something that would cause heat to be retained by the Earth and the surface of it more at night. Arrhenius in 1906 looked more at human-caused greenhouse gases, and he was a fellow Swede, so what do they know? Yeah, he kind of missed a few of the feedbacks that really were important to that mechanism, and those were brought to the forefront by Manabe and Weatherald in 1967, which is really what I consider to be the birth of the modern understanding of human-caused climate change. So again, that's nearly 50 years ago, which is surprising to a lot of people. I don't want to spend too much time on this figure, but this is some of the background, and actually I missed giving the credit for this figure, which is the Intergovernmental Panel on Climate Change. But this really depicts the mechanisms behind what's going on. The Earth has an input of heat from the sun and must eventually get rid of it. There's the pointer. Must eventually get rid of it by outgoing long-wave radiation. So long-wave radiation is the invisible infrared light that really is emitted from all sorts of solid objects around you and from greenhouse gases as well, not from non-greenhouse gases. And projected temperature changes in both the atmosphere and the oceans. These are projections at various times in the future, and it's shown the dimensions of each figure are latitude from 90 south to 90 north, and the height in the atmosphere here, which is expressed in terms of atmospheric pressure in this diagram. So for various times in the future, this has been studied by literally thousands of scientists around the world and accumulated in this report by the Intergovernmental Panel on Climate Change. This is actually the previous one. There's a new one that was released in 2013. Some of the issues with greater uncertainty related to climate change, and maybe this is sort of bad news for this audience, because these factors that give you greater uncertainty are the kinds of things that this group is interested in. So if it's more local relative to the globe, that's going to add to the amount of uncertainty that you're looking at. If it's more dependent on time variability, so that would be in terms of the contrast between something like average precipitation over a year versus frequency of storms. So the frequency of storms, as an example, would have greater uncertainty than the average precipitation. And then more links in the chain of causality. So the first link in the causality is the carbon dioxide or other human-caused greenhouse gases themselves. Then next link in the chain would be surface temperature and air temperature and a lot of interacting factors, and you might finally end up with fish population or growth, something like that. A lot of links in that chain of causality. Each of those links will have uncertainty associated with it. So some of my work on Great Lakes water levels, this is a chart of projections, and the timeline on this figure goes from 1999 on the left out to 2100 on the right, and a few different people have made projections of future Great Lakes levels. The green boxes show ranges of projected lake levels as projected by Angel and Kunkel, in 2010, and these generally show drops in lake levels relative to the present over here, but there is a range, and some of them are showing increases in lake levels. These green and kind of rust-colored dots over here are work that I did, and it's a comparison between two different methodologies of making these projections. And the older methodology, which is what was used by Angel and Kunkel, is showing, for this particular projection, it's showing a drop in lake levels, whereas using an alternative method that I think is more reflective of reality, it's showing rises in lake levels. So yeah, actually Lake Erie is on the bottom, Lake Michigan Huron in the middle. Michigan Huron generally has the largest signals in any sort of change in lake levels. But in any case, this is kind of an update on projections of lake levels, and it really does have serious consequences. So this is the assumed chain of causes behind those changes in lake levels that has been used for a long time. And so on the left here you have greenhouse gases, and then in the middle, air temperature and precipitation as a result of those changes in greenhouse gases, and then evapotranspiration on the right. A very simple set of pathways of causality. However, this is more reflective of reality. You have all these pieces of the system interacting with each other, and one of the equations that I showed on that previous slide quite a ways back about the historical development of pieces of the understanding of climate change was Helmholtz, 1872. I don't remember exactly the year, but the very simple chain of causality on the immediately previous slide I showed is severely transgressing against the laws of Helmholtz. So it had taken these results on the basis of that work, conservation of energy, and in trying to take this next step of saying, well, how much water is going to be left in the Great Lakes, it actually threw that physical law out the window and used some other methodologies that ended up having problems with them. So just to quickly go over algal blooms and hypoxia, there's been some work on this, but unfortunately it kind of ends up having a lot of those uncertainty issues that I brought up earlier. So mechanisms involving hypoxia and algal blooms include earlier and stronger thermocline, and then also stronger individual precipitation events are likely to be occurring in the future, and that could lead to increased nutrient loading into the lakes. So these are some of the arguments for increases in algal blooms and in hypoxia. So I'm sorry that I don't have a whole lot more to say about that. Some work on fish impacts, and I see at least one of my co-authors on this paper is in the audience. So these are some of the results of Cow et al. And this is using a bioenergetics model. This is really more directly relevant to Lakes Michigan and Huron. I apologize for that. But some of the projections of fish growth in the future is showing as long as you can maintain high consumption, if there's enough of a food supply for the fish, you get these black bars which show increases in fish growth. But then some of the other alternative scenarios have fixed consumption or reduced consumption, and those generally show reduced rates of fish growth throughout these regions. And I think this behavioral thermal regulation mechanism was gone over much more in the previous talk, but part of the idea behind it is if you have increased overall temperature, that means that you can have an increased duration of time throughout the year in which each species' preferred temperature is present somewhere in the water column. And one of the refinements in that's relevant to Lake Erie from the previous talk was, there's likely some difference among the western, central, and eastern basins of Lake Erie as far as how this mechanism might work over time. So, and especially in the western basin, I think because it's so shallow, you're likely not to get that fully developed thermocline and may not have the preferred temperature habitat for various species. So summary, warmer air and water in the future, possible drops in lake levels, not as large as previously thought. Changing seasonal phenology as far as the timing of stratification. Possible increases in hypoxia and algal blooms, and fish impacts may be positive, but that depends on having sufficient supply of food for them. And going back to the history of climate change, some of the people who have contributed pieces of the puzzle to it, got some of their pictures here. Most of them are lying in their graves. I, a few years ago, saw the grave of Euler over in Russia. Manabe is still living. He's 83 years old, and I understand he somewhat regularly goes into the office still. So that's the end. Questions?